Since 2012, when AlexNet came out, which was significant because this is what kicked off all of the kind of hype around deep learning. So that was about a 62 million parameter model. And now we have like 340 billion parameter models, even bigger. But since then, that's a 5,000x increase in the number of parameters. And that was trained on about a million images. I think it was like 1.2 million images. And now these are being trained on like 3.5 trillion tokens. So that's a 3 million x like increase in the data size. So we have a 5,000x increase in the algorithm, 3 million x increase in the number of data used. And so we need to keep up with that.
Hey, Brad.
Hey, how are you?
Doing well, sir. How are you?
Good. Another day in the AI way.
That's what they say.
Oh.
Well, today we're going to get back on the news beat, huh?
Let's do it. So we were debating because there was like a trillion news updates every second. And so we thought instead of doing all of them, which are all overwhelmed with, that we would just go deeper on the most important ones. And so there's 3 today that I'd like to cover. Let me share my screen. Okay, cool. So the first one is Voyager, really cool name, an open-ended embodied agent with large language models. So that's a handful. So let's break into why this is important and why this is meaningful and what the breakthrough was. So I'll just scroll it here to these kind of cool animations of Minecraft. So what makes Voyager important and why did I choose this one? So the cool thing is that, so Voyager uses GPT-4 and they said this didn't even work with GPT-3. So it just shows kind of the huge delta between GPT-4 and GPT-3. Yeah. So what Voyager does is it continuously improves itself by writing, refining, committing, and retrieving code from a skill library. So we'll go into exactly what we mean by that. But the main thing here is that it's writing code autonomously on its own and it's fixing code. And so this is interesting because it uses a new training paradigm, as you can call it. So why this is so interesting, and we'll go into some of the results, is so learning is important. It's obviously important for humans. It's important for AI. And so we're not quite sure how we learn, how humans learn. We know some details about Hebbian learning. There's a saying that neurons that fire together, wire together, but we don't know exactly how it works. And currently how AI deep learning learns is with gradient descent, which is basically an application of your high school calculus chain rule. And so why this is interesting is that it uses a new form of learning. So rather than Hebbian learning or gradient descent, it uses code. So they call it a no gradient architecture, which just means it doesn't use calculus. It doesn't use the calculus train rule. And so instead of doing this kind of typical way, it uses a code base that it's constantly writing to build skills for this character that's going on this voyage in Minecraft land. And the cool thing is the typical way people develop new algorithms is they start with games because it's a closed world, it's complex, but not so complex as the real world. So you can prove something in a scientific way. And in Minecraft, it achieves like over 3.3 times more unique items. It travels 2.3 longer distances, and it's like 15 times faster than the previous methods. So kind of a big deal in my mind. And while it's on a funny game, I've actually never played this game, but obviously it's a very popular game. It's a big breakthrough. So let's just go into kind of some of the things it's done here. And then I'll talk about why I think this is important in general and long term. So let's just look at this first graph. So on the y-axis here, you have number of distinct items. So again, I haven't played Minecraft, but from my understanding, you have tools and you have to collect things and build things, and it's fun. And then here's prompting iterations and code generation. So one iteration is you send a prompt to generate some code. And you can see that the orange is the Voyager without skills library. And then React, Reflection, and AutoGPT. These are other agent frameworks that also try to do things autonomously. And you can see that Voyager performs much better. I mean, let's just take 150 iterations. It looks like it's about 60 items it was able to get. Whereas the AutoGPT, which everyone's talking about, it's the rage, is around 20. So it's like 3 times better, at least in this.
So I have a question on this. How does it start? So it's sort of, they show all these examples of the agent moving through Minecraft and completing all of these various tasks. How does it start? Does a human ask it to do something, or does it come up with these directives on its own?
Yeah, good question. So we can kind of go into how it works in the components. That's actually the
Okay,
next
cool.
section. So it's a collaboration between human and AI, and they have a cool demo video of them building stuff. So the first thing is you have this automatic curriculum, and so it's things like mine with log, make crafting table, combat zombie, blah blah. This iterative prompting mechanism that can interact with code as actions, get feedback, and then the skills library, which allows them to harness this code base that they're going. So to answer your question, it starts, they have to create an agent that interacts with the Minecraft environment, and it needs some kind of reward mechanism. So they have to kind of give the agent dopamine, as it were.
Right.
And so in the beginning, it just kind of walks around mindlessly, and a human can say, hey, get me a diamond. So there is a human piece to it, but it doesn't need that. It can just walk around mindlessly until it accidentally mines something, and then it gets a little dopamine hit, and it's, oh, wow, they call it a reward. But you get this dopamine hit, and it's like, I want to do more of that. And this is kind of how humans work too, right?
Yeah.
So yeah, I don't know if that answered your question.
No, I think it makes sense. So it could aimlessly wander around and figure out how to do these things. And if it did, it would get the same reward as if a person was like, hey, build a table. Or if it just wandered around and then it built a table. And then through this, it kind of learns the basics of Minecraft, where you have blocks. And similarly, I haven't played it, but I understand kind of the core premise of the game is kind of this open world, and you can build kind of anything within it, which is sort of interesting because you mentioned at the beginning, like a bounding box is the game environment. And it's actually a pretty open-ended environment here that it has to experiment within.
Right. So they do give it an overarching goal of discover as many diverse things as possible. And based on that goal, GPT-4 generates a curriculum. So it has some inventory, and it gets information from the game, and then it generates reasoning. For example, since you have a wooden pickaxe and some stones, it would be beneficial to upgrade your pickaxe to a stone pickaxe for better efficiency. And then your task is to craft one stone pickaxe. And then it generates these skills to help you do that, and it gives feedback. Yeah, and then sometimes the code generates errors, and then it automatically fixes it. And so you can see that it's able to explore much more of the world than the other agents. Anyways, I think this is really cool. And maybe to kind of just touch on why this is bigger than just the game. So we talked about learning and having a new learning paradigm. But why I think this is important is this is a really interesting way to merge symbolic AI or symbolic reasoning and statistical AI. And so why is that important? So this is actually something I worked on in my PhD at MIT is merging symbolic AI and machine learning. But this is important because code and symbolic AI is good at some things and is bad at other things. So writing code is it's reliable. Like, it's a strong abstraction. It's mathematically verifiable. You can do like principled judgment. It can have logical reasoning, rules-based diagnosis. Whereas statistical learning is good at making intuitive judgments, finding patterns, classifying objects. And so they're very complementary, just in the same way human and AI are very complementary. AI is good at seeing patterns in massive amounts of data. Humans are good in looking at a limited set of data and making very deep, creative analysis. And so this is kind of a really interesting step in combining symbolic AI and statistical AI, which has kind of been a holy grail for a long time. And it's embodying this in this kind of autonomous agent, which is really cool. And so you can imagine that soon, first it's also, I guess, a little scary. First it's Minecraft, right? But soon you can imagine the next demo from, I don't know if you've seen those like Boston Dynamics robots where they have the little plot thing running around. Imagine that thing has human intelligence and reasoning and can do goals and not just run really fast.
Right.
So anyways, that's why I think this is important.
Yeah, it's super interesting. So the skills are kind of like hard-coded abilities that it learns, and the GPT-4 algorithm that's guiding it can reference these in the future, right? And tell it, hey, use this skill I taught you a ways back, combine it with this skill, and then accomplish this task. And so it kind of gives something that would otherwise bump into a wall at some point. It tells it what to do next. It's like, okay, now you know this and this. Next, you can combine it and you can do this. So I do think it's easy to see how this is kind of wild, and the potential is massive.
Yeah,
Obviously
and
beyond just Minecraft.
so just a bit of nuance. You said hard coded. It's actually just coded. It's soft coded. Like
Yeah.
it can update the code, it can change the code.
Right.
And there's been other demos of things like this, like reinforcement learning agents that also do cool things. But the new thing here is that you can actually write code, and you can imagine it can even modify its own agent code. And so the kind of code piece which they start implementing as a skill library and the prompting mechanism is kind of what I find super novel here.
So it could even take that skill and then augment it a little bit and say, now
Right.
use it. And it's different. Yeah.
Exactly.
Really cool.
Cool. All right, let's move on. So the second thing I wanted to talk about is QLoRA, efficient fine-tuning of quantized LLMs. So again, it's like, what in the hell does that mean? What's quantized? What's fine-tuning? So let's jump into why this is important. And I added some highlights here. So we know LLMs are, why they're important, Chat-GPT, blah, blah, blah. And we've all heard that that OpenAI has like $11 billion to do this. So super expensive, time-consuming, requires some of the most intelligent people on the planet. And so what this does is, let me just read this here. So they get 99.3% of the performance level of ChatGPT while only requiring 24 hours of fine-tuning on a single GPU. So let's take some of this with a grain of salt because it's their own paper. Did they really test it on everything? So take it with a grain of salt, but still really impressive when I look through the paper. So this is pretty game-changing in my opinion. And let's kind of talk about why. So QLoRA reduces the average memory requirements of fine-tuning a 65 billion parameter model from greater than 780 gigabytes of GPU memory to less than 48 gigabytes without degrading the runtime or predictive performance compared to a 16-bit fully fine-tuned baseline. Okay, so lots of words, lots of kind of jargon, but let me kind of break down why this is a big deal. So 65 billion parameter model is a big model. It's nowhere compared to GPT-4, GPT-3, but we're anyways learning that it's not just size that matters in terms of parameters, but there's many other things that go into this. And we heard Sam Altman talk about this as well. So there's kind of this new learning that it's not just the parameter count. It's just not just the size of your brain that matters. It's also how you train it, the algorithm. And so it used to take 780 gigabytes of memory. And so what that means is you couldn't train this on a single GPU. You'd have to have a whole farm, a whole compute cluster of GPUs, really complex algorithms to make sure you're sharing the memory, really expensive, really long time to train. And only very few companies, people have access to such a large GPU cluster. And so on less than 48 gigabytes, you can literally fit this on a single GPU. And I was just looking up some of the prices. So I think an A100, it's 79 cents per hour and it has 48 gigabytes of memory. So they mentioned they could train the 65 billion parameter model in 24 hours. So at 79 cents per hour for 24 hours, that's a little under $20 to train a 65 billion parameter model, which took Meta, for example, to train their Llama 65 parameter model. Like maybe, I mean, we don't know exactly, but it was single digit millions of dollars. So just imagine the democratizing power that this brings.
It's like smartphones are in our pockets, and they used to be these massive computers in a warehouse somewhere, and now you can have a little GPT-4 in your pocket for $20.
Exactly. And like a few weeks ago, I trained my own foundation model and it was 10K. And I was already blown away because 10K from 10 million is a huge difference. But now $20, it's like, oh my gosh.
I think a month ago we were talking about the Stanford one that they did for like $600, and we were like, wow.
I know.
No, it's $20.
It's amazing. The other interesting thing is what I was alluding to earlier is first we find that data quality is far more important than data set size. So for example, a 9K sample outperform a 450K sample on chatbot performance, even when both are meant to support instruction following generalization. So lots of really good news for the world in general. And we could go into detail about how they do this, but it's not super important. I would check out the paper if you're really interested. They do a good job in explaining it. But I was just really blown away by that. And they have an example here of its performance. So you can kind of make your own determination if you think it's 99.3 or whatever it said, the performance of Chat-GPT. So they have this, we'll link this, they have a demo of the implementation of that paper. They call it Guanaco. And so you can play with that. I said, tell me the meaning of life, and it generates Python code. But you can tell me if you think it maps to the paper. So the cool thing is this is all open source. Also Voyager earlier is open source. And so it's just a really great time to be alive. Like, I feel very grateful for all of this.
It's really cool. So did the advancements made by Facebook, OpenAI, Google, etc. unlock this for everyone else? Were they able to kind of, what's the relationship there between the work that they did and then the ability now for the open source community to build these super powerful tools?
So there was a leak of the Llama models, and whoever did that, bad.
Thank you, sir.
Yeah, exactly. I'm just like, I should say don't steal things, but it's like, also amazing, but yeah, I mean, anyways. And so what they're able to do is take that model and fine tune it. So they don't have to train it all from scratch, doing the next token prediction. And just having that in the open has just been an unbelievable Cambrian explosion of applications, of new innovations, of just passing on learning. Feels like the printing press moment, that when you put this in people's hands, you're just unleashing the collective creativity and intelligence of the human species. And it just makes me proud to be human. It makes me excited to be alive.
It's really cool. Thank you, Facebook.
Yeah. So the last thing I want to cover is the Nvidia Grace Hopper Superchip architecture. So we'll link the announcement. I like the CEO of Nvidia. He seems like a really down-to-earth kind of, he gives a lot of dad vibes, like he makes dad jokes, and he just seems like a really, really good guy. Okay, so what did they release? So they released a superchip. It's literally a supercomputer. It's not just the GPU. And so we'll go into some details here, but they essentially put 200 billion transistors, and you have one petaflops of compute on this supercomputer. And why this is interesting is this chip also has 600 gigabytes of memory. And not just that the CPU can access, the GPU can also access. This is shared across the GPU and CPU. And this may not sound like a big deal because you're like, whatever, I have 600 gigabytes on my computer. But until that point, the GPUs actually haven't been able to access that memory, that CPU high bandwidth memory that the CPU offers. And so there was just a lot of wasted time trying to load and offload large data sets and chunking them up into pieces onto the GPU. It's a really slow operation. And so now with this Grace Hopper chip, the GPUs can handle really, really large data sets. And it's using just kind of off the shelf, low power memory, the same memory that's in your cell phone. And so this is a big deal. And why is it a big deal? So I don't know if it's actually covered in this document, but I will just cover some of the results. So why this is important is there's kind of three big AI tasks right now. And this is massively speeding up that development. So for example, vector database search. So what is a vector database? So you have traditional databases where you store people's names and addresses, and this is text-based. You've probably heard of SQL before. So that's a traditional database. A vector database is what you do is you take a piece of text or an image or whatever, and you make it a vector. So a vector is just a list of, let's say, 10 numbers, thousands of numbers. So you have a number, which is a single dimension of number, and you have a vector, which is just a list of numbers in a high dimensional space. And so there's an algorithm, like you can use OpenAI's vector embeddings, but you can convert a piece of unstructured data like text, videos into this vector. And then what you can do is you can store that vector in a high performance database. And so this is one of the most important things we're all using now. And so it's 9 times faster on vector database search.
Wow.
Yeah. So killer, amazing, huge jump, almost a an order of magnitude jump. It's 12 times faster on recommender systems. So until kind of all this LLM stuff came out, recommendation systems were the most important applications of machine learning models, like powering trillions of dollars of revenue. Like you know why if you use Amazon or YouTube or any of these things, why recommendation systems, and it's 12 times faster on that. So you just don't see jumps like this. You're like, if you get a 1% improvement, that's like hundreds of millions of dollars of revenue for these companies.
Yeah.
So just 12x improvement is blowing my mind. And then it has almost 284, almost 300 times faster improvement on LLM inference. So like, imagine getting your GPT-4 results like 300 times faster. Just insane. So that's just kind of one thing that it just speeds up some of the most important AI applications. But even more than that, it continues this kind of Moore's law for AI. We've been talking about this, that every kind of 3.4 months, we're seeing the doubling compared to 2 years in the previous paradigm of Moore's law, doubling the transistors on the chip. You had traditional Moore's law, which is you count how many chips, how many transistors are on a computer chip, and it doubles every 2 years. And then we had kind of AI's equivalent of Moore's law, where the kind of compute power that AI can take advantage of doubles every 3.4 months. And so what's been an interesting result of that is since 2012, when AlexNet came out, which was significant because this is what kicked off all of the kind of hype around deep learning. So that was about a 62 million parameter model. And now we have like 340 billion parameter models, even bigger. But since then, that's a 5,000x increase in the number of parameters. And that was trained on about 1 million images. I think it was like 1.2 million images. And now these are being trained on like 3.5 trillion tokens. So that's a 3 million x increase in the data size. So we have a 5,000x increase in the algorithm, 3 million x increase in the number of data used. And so we need to keep up with that. And so this is a massive step in the direction of keeping up with this exponential progress. And I find it a really big deal. And I just wanted to show this. What they're going to do is actually not just release that chip, but let me just play it. He says it good. So he said they're going to connect 8 of these together.
Using NVLink. This is an NVLink switch. So 8 of this connect into 3 switch trays into 8 Grace Hopper pod. These 8 Grace Hopper pods, each one of the Grace Hoppers are connected to the other Grace Hopper at 900 gigabytes per second. 600 gigabytes, 900 megabytes per second, 8 of them connected together as a pod, and then we connect 32 of them together with another layer of switches. And in order to build
it's just ridiculous.
256 Grace Hopper Superchips connected into 1 exaflops.
Wow.
Exaflops. You know that nations have been working on exaflops computing and just recently achieved it. 256 Grace Hoppers for deep learning is 1 exaflop transformer engine, and it gives us 144 terabytes of memory that every GPU can see. This is not 144 terabytes distributed. This is 144 terabytes connected. Why don't we take a look at what it really looks like? Play, please.
This sort of answers a question I had about it. As you were talking about like vector databases and that, as I understand it, these are kind of the foundational elements that make a lot of this AI possible and make our data useful to us. And currently we rely on, let's say I wanted to spin up like a cloud vector database and use it to process my data. I'd be relying on like an AWS type service or something and using their servers. And, as you mentioned, they're not necessarily optimized for this type of activity. Whereas now what he's presenting here is basically the AI optimized version of these servers, where it's going to be way more efficient, way faster. It can handle way more data. It's sort of built for it. and stacking everything that we've talked about today on top of each other. It's just amazing because it really makes you see that idea that we talked about before where, yeah, it's going to keep growing and getting better. And it's happening in every way you can imagine. The big companies are continuing to just knock it out of the park with like greater improvements. The open source community is taking these little leaks, these little crumbs, and then turning that into like a world in and of itself. And then you've got Nvidia over here on the hardware side, just making the next step possible, because we've talked about before how even Sam Altman has mentioned that maybe just bigger and bigger isn't really the end goal. And so now we're kind of seeing like, oh, okay, I just never have seen in my life technology unfold before your eyes in such succession and so rapidly. I know technology accelerates quickly and it develops quickly, but for me, this is like next level in that like it's never been so where I can not talk to you about AI news for 2 weeks and then we reconvene and it's like, bro, where do we start? There's so much to cover. It's just amazing.
Yeah, there's we'll link it below, but there's a essay by Leonard Reed called iPencil. I think a lot of people have seen this, but we'll link it. Just watch it. It's really amazing, and it reminds me of this. And so he talks about this simple, dumb little pencil that we've all used in school, and then he goes into how the whole world is needed. Like people with different languages, different religions, different motivations, they all come together to build this pencil for you. And you just put your little quarter in the machine, you get your pencil, and he articulates it so well. And there's an animated version of it, and I love that because it reminds me of this too, and it reminds me of nature. And I just see all these amalgamations happening of just like, you see nature so beautiful. Like I watched this IMAX movie about the Serengeti, and they go into how the rain makes the wildebeest travel, and then that they eat all the grass and they have to move, and like nature's so connected. And then you have these dung beetles that take all the poop from the wildebeest, and then they re-till the soil, and you're just blown away. And then you see how big of a failure something like communism is, and you just see how big of a failure when you try to have these like centralized, controlled governments and things, and because they don't realize like you change one thing and you think you're changing one thing, but you're changing hundreds or thousands or millions of things. And so that's like, we're always seeing the bad side of that because everyone thinks the answer is like have government control it, try to control everything. Whereas if you just kind of surrender to the natural force of nature of the universe, then you start to see things like this, like Meta's sharing things, there's open source. Like I'm grateful for Google for sharing the original transformer paper, and then OpenAI is releasing, and then that triggers Nvidia to build the chips. And then you just have this beautiful nature ecosystem coming together in this amazing way, and it's wonderful.
It's pretty amazing. It's exciting, it's daunting, it's awesome in the true meaning of the word, and that it kind of does put you in awe, the pace of everything. But honestly, man, great news this week.
Yeah.
Unless there's anything else you wanted to talk about.
Let's call it a day.
Great chat, Brad.
All right.
Have
Cheers,
a good one,
man. Bye.
Bye.